Okay, let's go over practice test 3. So, first question. Give the critical value for confidence level 93%. Well, you know, if you have confidence level C, then ZC is just inv norm of 1 plus C, that whole quantity, over 2. Right? So here, I'm going to get Z sub 0.93 is inv norm of 1 plus 0.93 over 2. Now I always do this numerator in my head because otherwise I'll forget the parentheses that I need. So I'm going to rewrite this inv norm of 1.93 over 2. Right? And then I just take out my calculator and do the usual stuff. Let's see. So go to inv norm and then 1.93 over 2. And there I go, 1.81 approximately. Confidence level 8/9 is done the same way. It's going to be inv norm of 1 plus 8/9 all over 2. And I'm just going to do that whole thing in the calculator. I'm trying to get the glare off of it here. So inv norm of 1 plus 8/9 all over 2, I get about 1.59. Okay, number 2. A sample of 40 items is drawn from a large population known to be approximately normally distributed with standard deviation 907. The sample is found to have mean 13,205. Construct a 96% confidence interval for the population mean. All right, so what am I going to need? I need, let's see, a sample of 40 items, so n is 40. I'm going to use the calculator for this. I think that's obvious. The population is known to be normally distributed. That's nice. With a standard deviation of 907. So that standard deviation is for the population. So here I know sigma. It's 907. The sample has mean, so x bar is 13205. And my confidence level is 0.96. Okay, so I'm going to be doing a Z interval here. So, no, I don't want that. I want stat, then over to tests, and down to number 7 there, Z interval. I'm doing it with stats, right? So remember you have to choose, so I put it on stats and hit enter. And then I start putting in the numbers. Sigma is 907. X bar is 13205. N is 40. And my confidence level is 0.96. I'll go down to calculate. 12,910, 13,500. So that's the Z interval. Okay, problem 3. 500 samples of size 40 are taken from an approximately normally distributed population, and a 95% confidence interval for the population mean is constructed from each of the samples. About how many of the intervals constructed will actually contain the population mean? Well, what a 95% confidence interval is, what it means is that if you take a whole lot of samples and you construct a 95% confidence interval about each one, right, they'll all be the same size, about 95% of those intervals will contain the population mean. So about 95% will contain the population mean, mu. So 95% of, we have 500 samples, that's 475 of the samples. You can expect 475 of them to contain the population mean. All right, The lengths of a particular author's sentences are approximately normally distributed with standard deviation 4 words. What is the minimum sample size needed to estimate the average sentence length to within 2 words with 90% confidence? So what's the formula again? You have n, well, the approximation to n is z sub c times sigma over e, and then that whole thing has to be squared, and then you round it up to find your n, your minimum sample size. Okay. Here we have c is 0.9, so, you know, just like in the first problem, you use inv norm of 1.9 over 2, and you find z sub c is, what is it? I have it written down here, 1.64. Right, you round those off to 2 places, except in 2 little cases. So this approximation here becomes 1.64 times sigma, right? The standard deviation is 4 words, and then divided by e. And this is usually the hardest part of the whole problem. You must remember in these minimum sample size, right? They all say, what is the minimum sample size? In these minimum sample size problems, the hard part is to remember that E has to be given to you in the problem. You have to be able to look at the problem and find E. There's no way to calculate it for these minimum sample size problems. Here, you have to come within 2 words, so E is 2. E is how close you have to come to the population mean. So that goes here, 2. And then we'll square that. And if you do that on a calculator, you find out that it's about, let's see, again, I have it written down here, 10.7, okay, 10.7584, I think it's actually equal to that. So when you round up, that is 11. Okay. You must round up to the nearest integer. This will almost never turn out to be an integer. You have to round up to the nearest integer. Okay. Number 5. Jill, a busy girl, is collecting data to show that the average person does not take exactly 0.8 aspirin tablets per day, as is claimed by an article she read. So what is her null hypothesis? If she's trying to show that the average person does not take exactly 0.8 aspirin tablets per day, then her null hypothesis, H naught, has to be that the average person does take exactly 0.8 aspirins per day. Okay? So that's her O, and her Ha is mu is not equal to 0.8. I know the problem doesn't ask for that. Describe what it would mean for her to make a type 1 error. A type 1 error is when you accept your alternative hypothesis even though it is false. In other words, she accepts that the mean is not 0.8 when in fact it is. So this would be if she finds that the average is not 0.8 aspirin per day when in fact it is. She finds that her alternative hypothesis is true even though in fact it isn't. What would it mean for her to make a type 2 error? That would mean for her to accept her null hypothesis even though it's false. So that would mean that she finds that the average, sorry I'm hurrying here, is 0.8 per day, even though it's not. Okay. Number 6. Jean has correctly performed a hypothesis test and concluded that the average adult American man's hand is more than 180 millimeters long. So she has concluded that some average, the average hand size, is greater than 180. If a type 1 error occurred, which of the following must be true? Okay, you need to think through this. This is what she has concluded, right? And so this cannot be a null hypothesis. It must have been her alternative hypothesis. That means that her null hypothesis was less than or equal to 180, right? because it has to be the negation of the alternative. So if she accepted her alternative when it wasn't true, that means that the null hypothesis was true, and that in fact the average size is less than or equal to 180. So the average length is no more than 180. That is the correct answer there. Right? That's the thing that has to be true if what she concluded was a type 1 error. All right, for each null hypothesis H0, write HA. So if H0 is mu is less than or equal to 100, then this is mu is greater than 100. I assume you can all do this easily by now. Equal, mu is not equal, greater than or equal to, less than. Oops, mu is less than 100. All right. On to number 8. The numbers below represent a random sample. Okay, there they all are. Part A. How could you tell whether it was okay to construct a confidence interval for the population mean for this sample? Well, there are a couple of ways. First of all, it's fine if you have at least 30 data points, right? And you do here. You have more than 30, so you're groovy. You can construct a confidence interval. Another thing you could do would be to, use a QQ plot to see whether the data looked like it was from an approximately normally distributed population. But simply having n greater than or equal to 30 is fine. Right? We need n greater than or equal to 30, which we have. Okay. Construct a 92% confidence interval for the population mean from this sample. Give your interval endpoints to the nearest thousandth. All right. So how do you do this? Well, you probably know by now, but here's the procedure. First thing you do is you go into the stat edit thing and you put all of your data in list L1. Now that's really tedious to watch someone do, especially in a video. So I've already done it. Right? Once you do that, you just want, this is going to be a t interval, right? You don't know the population standard deviation here. All you have is a bunch of data. So this is going to be a t interval. So we're going to go to stat, over to tests, and then down to t interval, which is number 8 down there. We're going to do a t interval from data. So I'm going to switch this over to data and press enter. And when you do something from data, all the stuff you need, except for your confidence level, is going to be computed for you from the data. So all you have to do is go down and set the confidence interval. Notice that list is set on L1. It has to be if your data is in list L1, as it should be. Freq here should be 1. Don't touch that. Confidence level. What confidence level are we supposed to do? 92%. So I'll put in 0.92 here. Oops. Right. 0.92. And then just go down to calculate. And in a few seconds, Bob will be my uncle. 68.253 and 70.206. Okay, number 9. Jake claims that the average income of a family of 4 in America is $56,516. It's just about right for this year or last year. But Jenna disagrees and is doing a survey to show Jake that he is mistaken. What should her alternative hypothesis be? Right? Jake claims, essentially, that the average, which I'll call mu, is equal to 56516. Jenna wants to show that he is mistaken, so her alternative hypothesis, her research hypothesis, should be that mu is not equal to that number. That's her alternative hypothesis. All right, give the conditions required to use a z-test. Right? You must be able to use the CLT, that is, you have to have n greater than or equal to 30, or the population approximately normally distributed, and you must know sigma, the population standard deviation. To use a z-test, you have to be able to use the CLT, and you must know the population standard deviation. give the conditions required to use a t-test. Well, you must be able to use the CLT. Right? And you should not know sigma. If you do know sigma, you should just go ahead and use Z. All right, problem 11. A magazine article claims that the average house cat can jump no higher than 6 feet. So the claim here, there's a claim that the average is less than or equal to 6. A reader has gathered the following jump heights in feet from his friend's cats. And there they are. Assuming that jump heights are approximately normally distributed, test the magazine's claim at the 0.05 significance level. Write your hypotheses, give the p-value you find, and state your conclusion clearly. Well, our hypothesis, the only hypothesis we can really have is this right here, this claim, right? So our H naught is going to be mu less than or equal to 6. Note that that couldn't be an alternative hypothesis, right? Because of the less than or equal to. HA, the alternative hypothesis is mu is greater than 6. All right, let's get a p-value. What are we going to do here? Oh, first of all, I should say that we can do a test here. Even though we only have a few data points, we can do a test here because we're told that the jump heights, which is the population here, are approximately normally distributed. All right, so let's get a p-value. All I'm going to do is I'm going to put this data in list L1, which I've already done here. And then I'm going to go to stat, over to tests, and choose t-test. Of course, I have to choose data because I'm doing a t-test on data. Right? And when you choose data, everything is calculated for you from the data, the standard deviation, which is, of course, a sample standard deviation, and the mean are calculated from the data. So all you have to do here is put in mu naught, which in this case is 6, and then go down here and choose the alternative hypothesis. As always, leave list to L1 and freak to 1. Now what's the alternative hypothesis? We said it is mu greater than mu naught, so there we'll choose that one. Then we'll go down to calculate and hit enter. All right, so we got a p-value here of about 0.066. So p is about 0.066. We're testing at the 0.05, so alpha is 0.05, the 0.05 significance level, and since this p, 0.066, is greater than 0.05, we can't reject H naught. In words, you'd have to say something like this. This data does not support a claim that the average house cat can jump higher than 6 feet. Okay, let's do the next one here, number 12. Suppose that a population is known to be approximately normally distributed with a standard deviation of 120. A claim is made, so let's see, approximately normally distributed with a standard deviation of 120. We're being given sigma here, the population standard deviation. It's 120. A claim is made that the population mean is at least 950, so the claim is that mu is greater than or equal to 950. That's going to end up being our null hypothesis. And a sample of 35 items, so hold on, I'm going to write n equal 35. A sample of 35 items is found to have a mean of 915, so x bar is 915. What is the null hypothesis? Well, the only possible null hypothesis here is that the mean is greater than or equal to 950. So I'm going to write H naught, which is mu greater than or equal to 950. And of course, I'm going to also write HA mu less than 950. Because that's what I'm going to have to put in a calculator when I go to do a test. Okay. Could H naught, the null hypothesis, be rejected at the 0.1 level? Well, we got to get a p-value to find that out, right? So let's go ahead and do that. What am I going to do? I'm going to go to Stat, Tests, and this time I'm going to be doing a z-test because I've been given the population standard deviation. So I'll choose z-test. I'm not doing stat data this time, I'm doing it from stats. All right, so let's put these numbers in. Mu naught is 950. Sigma is 120, it's already in there. X bar is 915. N is 35. Should have mentioned that. But we're told that the population is approximately normally distributed anyway, so we could have done a test even if n were less than 30. And now the alternative hypothesis, we've said right there, is mu less than 950, so let's go ahead and choose that, mu less than mu naught. Then we'll go down to calculate. P is about 0.0422. Right? So P is about 0.0422. Can we reject the null hypothesis at the 0.1 level? Yes. When alpha is 0.1 and P is 0.0422, P is less than alpha, so we can reject. Yes. Can we reject it at the 0.05 level? Yes. We still have 0.0422 less than 0.05, so yes, we can. Can we reject it at the 0.01 level? No. This number 0.0422 is not less than 0.01, so we could not reject it at the 0.01 level. Problem 13 here. A car company claims that its pulsive model averages 38 miles per gallon. So the claim here is that mu is equal to 38. Averages 38 miles per gallon on the highway. To test this claim, 32 traveling salesmen, okay, I'm just going to make a note, 32 traveling salesmen were asked to keep track of their mileage for the month. The mileages they reported are given in the table below. Using that data, test the company's claim at the alpha equal 0.1 level. Give the p-value you find and your conclusion. Well, we have a large enough n to be able to use the central limit theorem, so we can do a test here. It's going to be a t-test because we have sample data only. We don't have anything about the population standard deviation. So what we're going to do is we're going to put all that data into, into list L1. I've already done that, as you can see. And then we're going to use t-test. So we're going to go stat tests and then choose t-test. We're going to do this t-test from data. Mu naught is 38. We don't touch either of those. And the claim here, and I probably should have written this down, our null hypothesis is going to be mu equals 38. And so our alternative is mu not equal to 38. Pretty much the only thing that could be chosen here. Mu is not equal to mu naught. If we go down and calculate, we find P is, now read this carefully, it looks like P is bigger than 1. P is a probability, so it can't be bigger than 1. What does that mean? That means I better read all the way to the end. This is 1.164 times 10 to the minus 4th. So P is about 1.164 times 10 to the minus 4th. And that means I'm going to take this decimal point here and move it 4 places to the left. That is, P is approximately 0.000164. Okay, that's a pretty small p. Well, alpha is 0.1, right? So certainly p is less than alpha. So we want to reject the null hypothesis. We could write this in words by saying something like, this data does not support the claim that the average mileage is 38 miles per gallon. Okay. Number 14. Which of those graphs has R equal minus 0.9, which has R equal 0.1, and which has R equal 0.85. Well, let's take a look. This first graph here, we have data. It's not really close together, but not far from a line. If you were going to draw in the trend line, it probably looks something like that. Right? So the data is fairly close to the trend line, and that trend line slopes down, which means R is going to be negative. Right? The data slopes down from left to right, then R is going to be negative. The only one of these R's that's negative is this, so this one has to have R equal minus 0.9. Okay, let's look at these other two. One of them is going to be 0.1, the other one's going to have R equal 0.85. This one, it's hard to guess what the trend line will be altogether because it's so scattered, but it looks like it might be, with a little more data up on the top, it might be something like that. In any case, the data is not going to be very close to the trend line altogether. So it's probably this R equal 0.1. But just to be sure, let's go over here and look at this one. Yeah, this data you see is much closer to a trend line. That trend line also slopes up, but these data points are going to be, in general, much closer to this trend line than these data points are to this one. So this was going to be 0.1, and this one's going to have R equal 0.85. All right, let's do number 15. This is a linear regression plot. The table below shows several prices per barrel of crude oil and corresponding prices per gallon of gasoline, both in dollars. And the first task here is going to be find the equation of the regression line using oil price, the top row there, as the independent variable. Round coefficients to 3 decimal places. All right, so what do? This is strictly a calculator exercise. You put the data, you go to Stat, Edit, and you put the data, the oil price data in list L1, and the gas price data in list L2, just as you've been told to do. And then you go to Stat, over to Calc, and choose number 4. There you go. And it gives you A and B and so on. So A is 0.0359 to 3 places. A is 0.036, and to 3 places B is 0.088. No, it isn't. It's negative 0.088. So the equation of the regression line is going to be y equals 0.036x minus 0.088. All right. Use the trend line to predict the price of gas when crude oil costs $57 a barrel. Round your answer to the nearest cent. Well, all you want to do there, right, what you have here, is you have a formula where you put in the oil price and you get out the gas price, so the predicted gas price, right? So if you want to know the predicted gas price when oil is $57 a barrel, you just plug in 57 for X. So you should get 0.036 times 57 minus 0.088, and that is, let's see, about $1.96 when you round to the nearest cent. Okay, to 2 places, what is the correlation coefficient R? You just read this right off the screen. It's about 0.98. Right? And finally, about what percentage of the variation in gasoline price is explained by crude oil price? Right? Round your answer to the nearest integer. Well, all you got to do is you got to find R squared. Right? R squared is about 0.96. R squared is about 0.96, which means that about 96% of the variation in gas price is explained by oil price, which is what you'd hope for, right? the gas price ought to track the oil price pretty closely, or someone is fooling around with the prices. The body temperature of healthy humans is approximately normally distributed with mean 36.8 degrees C and standard deviation 0.4 degrees C. If a sample of 24 people is chosen at random, what is the probability that the sample mean will be between 36 and 38 degrees? So we're looking for the probability that x bar, not x, but x bar, is between 36 and 38. So for x, so this is just going to be a normal CDF. 36 and 38 are the left and right endpoints of the interval we're interested in. Right? We're looking for probabilities about x bar, so we need to be thinking about the mean and standard deviation of the x bar curve. Right? So mu x bar is just going to be mu, right? And that's 36.8. Sigma x bar is going to be sigma over the square root of n, and so that is, what is it, 0.4 over the square root of 24. So that's what goes in here. Mu is 36.8, and this is 0.4 over the square root of 24. And I don't think I need to do that calculation in front of you. You end up with about 0.9928. So the probability that is the mean of a sample of that type in that situation would be between 36 and 38 degrees is 0.9928. All right. Number 17. Janet has 42,000 bags of potato chips in her warehouse. The number of chips in a bag is approximately normally distributed with mean 700 and standard deviation 32. For a sample of 50 bags, we have mu x bar. Well, mu x bar is just going to be mu, so that's 700. Sigma x bar, we know that that's sigma over the square root of n. In this case, that is 32 over the square root of 50, which is approximately 4.525. About how many bags can she expect to hold between 640 and 760 chips? What we're going to do is we're going to find the probability that if you chose a bag at random, it would hold between 640 and 760 chips. And then we're going to say, well, the only way that the probability can be that number is if a certain fraction of the total number of bags has between 640 and 760 chips. So first, what's the probability that 640 is less than or equal to x is less than or equal to, what is it, 760? Right? Here, x is number of chips in a bag. Right? So the probability x is between 640 and 760. That's just going to be a normal CDF, right? 640 to 760 with mean 700. Right? And now we're not looking at a sample or anything. We're just wondering about bags. So the standard deviation here is 32. And that turns out to be, let's see, what does that turn out to be? I have it here somewhere. 0.9392 approximately. Okay, the only way that if you chose a bag at random, the probability that that bag would hold between 640 and 760 chips was 0.9392. The only way that happens is if about 93.92% of the bags have between 640 and 760 chips. So about 93.92% of the bags have between 640 and 760 chips. I'm not done, however, because what I was asked was about how many bags. Right? So I have to find 93.92% of the total number of bags. And I'm just going to go up here and do it. Right? 93.92% of her 42,000 bags That's 0.9392 times 42,000, which is about 39446 to the nearest integer. All right, problem 18. An experiment finds a sample mean of 45.32 for a sample of size 50. A hypothesis test is conducted to determine whether this result constitutes strong evidence that the population mean is greater than 45, and that test finds a p-value of 0.041. Now, a p-value is a probability. Exactly what is this p-value the probability of? Probably the easiest way to understand this is to draw a picture. So here's a picture. This is a picture of the x-bar curve. And let's see, this experiment was conducted to find out whether a particular sample mean, 45.32, constituted strong evidence that the population mean is greater than 45. So this x-bar is normally distributed, and the mean is going to be 45. The mean of the population is hypothesized to be 45, and so, of course, the mean of the sample means is also 45. 45.32 will be some number about right there, let's say. It's going to be to the right of 45, wherever it is. All right, what is found is a p-value of 0.041. Remember that means that the area to the right of 45.32, this particular value of x-bar from this sample, that area right there is 0.041. So you could write this by saying the probability that x-bar is greater than 45.32 is 0.041, and that would actually express what p is the probability of here. That's the p-value. It's the probability that the mean of a randomly chosen sample in this situation would be at least as large as 45.32. Okay, 19. Jared read in a textbook that if ductile iron is subcritically annealed, then its Brinell hardness will not exceed 170. Due to some issues at work, he has begun to doubt this claim. To test it, he measured the hardness of 35 pieces of subcritically annealed ductile iron, for which he found a sample mean of 173.6 with a standard deviation of 1.05. Should he now use a z-test or a t-test, or can he use neither? Okay, so first of all, can he do any test at all? Yes, he can use the CLT. Right? He can do a test because he can apply the CLT, because his sample size is at least 30. Which test can he do? Well, if you read this, it says he found a sample mean of 173.6 with a standard deviation of 1.05, right? So the standard deviation is from the sample, not the population. It's from the sample, so he must do a t-test. Okay. Oops, this way. Problem 20. And it says here that this is a hard one. And it's a hard one because the answers are very long. Germain tested the hypotheses H0, mu is less than or equal to 365, and HA, mu is greater than 365, using a sample of size 88, for which he found a mean of 367 and a standard deviation of 7.1. Which of the following statements is correct? All right, so hold on. Before we even get to the answer, let's talk about this. We have our hypotheses here. That's easy, right? And so we would have mu naught is certainly 365. We have n, the sample size is 88. X bar, the sample mean is 367. And let's see, the sample has a standard deviation of 7.1, so S is 7.1. So the standard deviation we have here is from the sample and not from the population. Let's go ahead and do this test. Right? So we're going to, since this is from the sample, since the standard deviation is from the sample, we're going to do a t-test, right? And we're going to find a p-value. So let's go ahead and do it. We're going to need it. So, okay, so let's do stat tests. We're going to do a t-test. We're going to do it from stats. Okay, mu naught is 365. X bar is 367. The sample standard deviation is 7.1. N is 88. And our alternative hypothesis is mu is greater than 365. So I want to go down here and choose greater. Calculate. And I get a p-value of 0.0048. Okay, so p is approximately 0.0048. All right. Oops, is that true? I don't see a 0.0048 here. That's why I'm asking. Oh, 0.00487. So this would be 0.0049 approximately. Okay. So which one of these answers is true? We'll just start with A and go down. Which of the following statements is correct? A, if the true population mean is no greater than 365, right? So that's the null hypothesis there. He's saying that if the null hypothesis is true, if the null hypothesis is true, then the probability that the mean of a randomly chosen sample of size 88 is at least 367 is approximately 0.0049. Okay. This is about the meaning of a p-value, right? What does a p-value actually mean? What is it the probability of, just like in the previous problem? Well, the p-value is the probability that if the null hypothesis is true, and you choose any sample at all of the same size as the one you chose, then the probability that that sample, that the mean of that sample is at least as far away from mu naught as the mean you actually found before, your 367 in this case, that's the p-value. So since the p-value here is 0.0049, this is saying if the null hypothesis is true, then the probability that the mean of a randomly chosen sample of the same size as the one you chose before is at least as far away from mu naught as your mean, right? So at least 367. But that probability is 0.0049. This is the correct answer. We don't need to go any farther. Okay. It's a little hard to say that stuff in a few simple words. You just have to think your way through it. All right, so let's do this. Last one. Jean has correctly conducted a hypothesis test for the mean of a normal population using these hypotheses. Mu is less than or equal to 31, mu is greater than 31, and an alpha of 0.05. She found a p-value of 0.03254 and rejected the null hypothesis, which she should have because p is less than or equal to alpha. The true population mean, however, is 30.93, which you'll notice is less than 31. Right? She rejected the null hypothesis, which means she accepted her alternative, right, that mu is greater than 31. And you can see that that really wasn't true. Right? It looked like it from the evidence she got from her sample mean, but it wasn't true. The true population mean is 30.93. Okay, mark each of the following statements true or false. There is evidence to show that mu is greater than 31. That has to be true. And the reason it has to be true is that otherwise Jean would not have done her test. She must have had an X bar greater than 31, or it would not have made sense to conduct this test. Okay, there is not evidence to show that mu is greater than 31. Well, that's the negation of the thing there, so that's got to be false. There is evidence to show that mu is less than or equal to 31. Well, presumably somewhere there is, or she wouldn't be bothering with this, but she doesn't have it. We don't know that she has it. We don't really know that it even exists, but for some reason she thinks that it needs to be tested. Jean has proved that mu is greater than 31. False. Sample evidence never proves anything. It only indicates which of two hypotheses is more likely. Jean has not proved that mu is greater than 31. That's got to be true. Jean has proved that. False. Doesn't matter what it is, Jean hasn't proved it. Jean has not proved anything, so she hasn't proved that one in particular. A type 1 error has occurred. Okay, what does that mean? A type 1 error occurs, right? Type 1, you accept your ha when it is in fact false. Her ha was mu greater than 31, and she did accept that, right? She rejected the null, which means she accepted her ha. But her ha was false, right? Because the true population mean is only 30.93. So yes, a type 1 error has occurred. When does a type 2 error occur? Type 2 is you accept your ho when it's false. Well, she didn't accept her ho, so that couldn't have happened. So that statement has to be false. All right, that's the whole shebang. I hope it helped.